Electronic Specifier.
Welcome to Electronic Specifier Insights, the podcast for electronics engineers. I'm your host, Paige West. In today's episode, I speak with Andrea Banfi, Business Development Manager for EMEA at Vicor, and Gerald Angerer, Lead Hardware Engineer at Microgate, about enabling deep space exploration with colossal telescopes. One of the biggest players in the field, the European Southern Observatory, is an intergovernmental research organisation made up of 16 member states for ground-based astronomy, and is working with Microgate to build the largest among next generation of extremely large telescopes. You'll also learn how Microgate is working with Vicor to power this fantastic application. We hope you enjoy this episode. Let's get started. I'm your host, Paige West, and today I'm pleased to be joined by Andrea Banfi, who is the Business Development Manager for EMEA at Vicor, and Gerald Angerer, who is the Lead Hardware Engineer at Microgate. So thank you both very much for joining us. I'm going to ask each of you to introduce yourselves for me. So Andrea, why don't we start with you?
Thank you, Paige. My name is Andrea Banfi, and I've been working in Vicor since April 2022. In my role as a Business Development Manager, I take care of sales and first technical support to customer in EMEA for Vicor products. Previously, I gained experience in power conversion industry, both as a power supply designer and working in company developing electronic device for power supplies.
Fantastic. Thank you very much. And Gerald, what about you? Why don't you tell us a bit about yourself?
Yeah, hello, everybody. My name is Gerald Angerer. I'm working with Microgate since 2007. Before I joined Microgate, I was working in the frequency converter industry, so together with DB Woods. Then at Microgate, I became responsible for hardware development in general terms. This includes power conversion, digital design also, and finally, I get responsible also for analog circuitries. Working place at Microgate here is very various, and I appreciate this working place.
Good, fantastic. Thank you very much. And why don't you both tell us a little bit more about the companies you work at? Andrea, I think our listeners are quite familiar with Vicor, but why don't you give us a bit of a company overview?
Yes, but Vicor can say that with over 40 years of experience in designing, developing, and manufacturing power modules for the most demanding markets, Vicor today is a leader in high-performance power modules, aiming to help our customers develop innovative solutions for modular power systems that are easy to use in power distribution network and offer maximum density and efficiency from source to point of load. Vicor power modules continuously improve power density, efficiency, and delivery capabilities while remaining at the forefront of distribution architectures, conversion, topology, and packaging technology. Vicor have customers in the area of enterprise and high-performance computing, industrial automation, automotive, robotics, UAV, electrical vehicle transportation, satellite, aerospace, and defense.
Fantastic. A great introduction. Thank you. And why don't you tell us a little bit more about Microgate as well, Gerald?
Yeah, Microgate was established in 1989 by the brothers Vinicio and Roberto Biasi. So the second one, Roberto, is still today the CTO of Microgate. So it's important to know that Microgate's first reputation is in the field of building and developing and producing high accurate chronometers, so timing devices for professional sport activities. This activity was related to the experience and the activity of Roberto in ski racing at professional level. So he built up the first chronometers, taking device with him for the training activity, showing to the trainers. And in this context, they asked him to produce also for other teams the same devices. And this was the birthday of Microgate. So the timing division of Microgate was related to the skiing activity of my boss. And in the next steps, then Roberto's PhD activity was associated to development of very compact sized linear motors. So these linear motors then, together with an Italian famous professor, Piero Salinari, was accumulating in the development of the first adaptive mirror. So it's a mirror using the adaptive optic concept, which means, we will hear later maybe, that deformable mirror improves the quality of the seeing. Still now, the Microgate houses these two divisions. So one division related to performance, timing, and sport activities, and the second one, the engineering group, dealing with adaptive optics.
Fantastic. What a great backstory. So thank you very much. And I'd love to chat today to both of you about enabling sort of deep space exploration with colossal telescopes. And one of the biggest players in the field is the European Southern Observatory, which is an intergovernmental research organization made up of 16 member states for ground-based astronomy. And I understand that they're working with Microgate to build the largest among the next generation of extremely large telescopes. But before we dive into that, Gerald, for your opinion, tell us what sets Microgate's sort of technology apart from other companies out there.
Okay, so at first, just to give a detail maybe of interest, our technology, which is dealing with the deformation of these thin mirrors, the thickness of the mirrors that we are talking about is about 2 millimeters. So our technology allows that the mirror is completely floating on a magnetic field. So there are contactless motors. We have no mechanical joints together with the mirror. Saying this means that if we have to deal with faulty motors, so with with the fact that some motors fails, we are not constrained to interrupt the observation of the telescope because of contactless solution. So this is, I would say, one of the key aspects of our technology.
Fantastic. And sorry, was there anything else you wanted to add?
Yeah, it's just then to give. So at the moment, we can state that we have a unique role in the development of these adaptive large mirrors. So we are a little bit free of other, of the pressure of other companies.
Excellent. Thank you for explaining that for us. And going back to what I said earlier then, can you tell us about how you are working with the European Southern Observatory?
Yeah, as you stated correctly before, the European Southern Observatory is the intergovernmental research organization here in Europe with the 60 member states. And so we can state that ESO it's the acronym for European Southern Observatory, is our customer in terms of providing all the necessary specifications for building the deformable mirrors. Of course, the overall telescopes are large structures, so with a lot of sub-suppliers, so with a lot of other companies involved in this segment. And the Microgate is working with all the stuff that has to dealing with the correction of the seeing, so with the deformable mirrors. Okay, so we can say that the deformable mirror, called also DM, deformable mirror, it's a crucial element of the telescope, because the dimension, the big dimension of the telescopes can be only used meaningful if seeing will be corrected with adaptive optics. Otherwise, it makes not sense to build them always greater and bigger, because the collected light suffers from the distortion of the atmosphere. And in this context, we are in a concurrence, let me say, with what we call the space telescopes. For example, with the Hubble telescope. But the ESO organization is related to terrestrial astronomy, ground-based astronomy should be the correct term.
Excellent. What a fantastic case study. And focusing on it in a bit more detail. Can you sort of describe the challenges that you faced and tell us how you've overcame those?
Yeah, so the correction of the distortion of the disturbances arriving from the atmosphere. So you can imagine that the light is traveling from the star that we will observe through the atmosphere to Earth, and passing the atmosphere, the wavefront. So the image the image is disturbed by the atmosphere turbulences, and to correct these turbulences, we have to perform wavefront correction in terms of a physical approach. So it's not a filtering. We physically we geometrically better deform the mirror shape in order to correct the wavefront and to get a planar wavefront again for the camera observation. So saying this, the unit requires a thin mirror with possibility to be deformed in a very fast and in particular in an accurate way. Fast means that atmospheric aberrations can vary very fast. in terms of time. So we have to deal with milliseconds. This means that the overall geometry, the overall shape of the mirror should be set to the new shape within a few milliseconds. And in fact, the challenge actually that we arrived in a consolidated way is 1 millisecond. So each millisecond, the overall mirror gets a new shape imposed in such a way by the control loop that overall system receives an excellent image quality. Just to give an information maybe about the number of actuators involved in this activities and the deformation, you can imagine that mirrors that we are talking about are 2.4 diameter in dimension, but I'm talking now about the deformable mirror. Instead, the principal mirror, so the primary mirror, is 39 meter in diameter as extension. Okay, so just to give you an idea of the dimension of the telescope. So on the deformable mirror on our side, we have to deal with 5,400 motors that will be controlled and powered synchronously and completely in parallel. And we have to set the shape with a precision of a few nanometers. So we have collocated sensor systems allowing this precise and very accurate shaping of the mirror. So challenging in this context is certainly, let me say, the design related to the analog circuitry. We have to deal with a very good noise behavior of the measurements because measuring nanometers is not as easy. And the second challenge certainly lies in the fact that we have to put an amount of 10 kilowatt, talking about power, into the mirror to get him deformable. So the stiffness of the glass itself requires about 10 kilowatt to be deformed in the accurate way. And saying this, obviously what we need is a very high concentrated power supply architecture close to the mirror, because we cannot allow us to deal with cabling, because each additional watt dissipated in the circumstance of the mirror contributes to an additional aberration of the image. So the image suffers from local thermal aberration, thermal dissipation, and therefore we need highly reliable and certainly high efficient power supply units that are cooled in this case by a gas cooling system. So no dissipation in air. We have cold plates that are gas fluided, and the gas is taking away all the dissipated heat generated by our electronics from the circumstance of the mirror.
Fantastic. And speaking of power then, why don't you tell us sort of how you're working with Vicor and what that partnership's like and sort of how you're using their modules in this application?
Yeah, certainly Vicor has a unique role for us. We had a lot of experience using their module also for other applications. Certainly not what I call the high density modules that we are using actually. Maybe Andrea is giving more details later. But our requirement was a very high power density in terms of watt per inch square. And saying this, we need about 150 watt for the motor group that we group it in 36 channels. And just Vicor at the moment, I would say, as a unique supplier, provides these modules with this high power density combined by a very good efficiency also at a moderate power consumption. So this was the trigger to introduce the Vicor modules in this project. Certainly the past experience showed us that the reliability, so the availability of the modules itself and failure-free working behavior is an excellent characteristic of their devices.
Brilliant. Thank you. And Andrea, coming to you then, what are your thoughts on this application and the use of Vicor modules? And what would you say make your modules particularly suited for this application?
First of all, I want to thank Gerald for the good word about our product and generally. The feedback from our customer, it's fundamental for us. Speaking about our module, Vicor modular power solutions are specially designed to meet the needs of the most advanced application, and the one from Microgate is absolutely on the head. 3 characteristics I want just to mention in this context. The first one that is one of the key factors for our product are the power density. In advanced application like the one of Microgate, where every cubic centimeter count and size is critical, our modules are optimized to offer maximum power in the smallest possible space. Just to give an example, the DCM3623 module used by Microgate is capable of processing a power of over 400 watts. Another aspect is energy efficiency, which is an imperative in many areas. Vacuum module operating at a very high efficiency, minimizing losses and minimizing the needs for bulky cooling system. This results in lower energy consumption and higher system reliability in the long term. The third characteristic that I want to mention here is the robustness and variability. This is one of the characteristics already mentioned by Gerald. Advanced applications require robust and durable solutions, and our modules are built to operate in extreme conditions, withstanding vibration, temperature fluctuations, and other environmental stresses. This translates into increasing durability and reducing maintenance cost.
Excellent. And Andrea, sticking with you for a moment then, what was the collaboration process like between Vicor and Microgate? You know, were there any unique innovations or customizations that you made to adapt your modules to meet Microgate's needs?
Yes, this was a very important aspect of our collaboration. Our success with Microgate was the result of a really close collaboration. We worked together with their engineers to fully understand their specific needs. Thanks to this continuous dialogue, we were able to improve our solution to perfectly meet their requirements. For example, and Gerald maybe can say something about, we were able to their valuable feedback on this by further reduction of the output voltage ripple to almost imperceptible levels.
Fantastic. And Andrea, you know, you've mentioned it already, but scalability is crucial for projects like these. So how do your power modules scale to meet the needs of increasingly complex and power intensive applications, such as those in deep space exploration?
Today, power system designers are increasingly looking for a flexible solution, and the Vicor module power approach is the answer. It's like having a set of bricks with which to build the perfect power delivery network for every project. Usually, an initial budget on system power is made in the early stage of the design. It happens, however, that during the development, requirements may change. With Vicor module power approach, it's easy to adjust and adapt the power delivery network to new requirements. The beauty of Vicor modular power system is precisely the adaptability. Even new requirements emerge during development, you can simply replace or add modules to optimize the power delivery network without having to redesign everything from scratch.
Excellent. And space applications often bring unique challenges, should I say, such as harsh environments, thermal management, and efficiency requirements. You know, some of these we've mentioned already, but how does Vicor address these specific challenges in its power solutions?
Vicor modules are designed to operate in extreme environments, withstanding thermal shock, vibration, and ionizing radiation. By using high-quality material and rigorous testing, we ensure the highest reliability of our product modules. We have optimized thermal dissipation of our modules using innovative solutions to ensure efficient operation even under high-load conditions and simplify heat extractions. For example, in the DCM3623, heat is equally distributed on the top and the bottom surface of the power modules, allowing greater flexibility in thermal design. Vicor relies on patented resonant power conversion topology that not only ensure high energy efficiency by reducing losses and minimizing heat generation, but also have a less impact on the electromagnetic interference. This results in a simpler design of both the thermal dissipation and the filtering part against electromagnetic interference. In particular, I think this is an important thing about an application with a very advanced application. These characteristics help our customer to design their system looking at the longer life and reliability of the system itself.
Fantastic. Well, I think this application is really fascinating. And Gerald, thank you for taking the time to share the details with us. It's also a great case study of Vicor's power solutions. But before we wrap up, Gerald, was there anything else that you wanted to say? Anything you wanted to add?
Just to wish all the teams working for the European Southern Observatory that they will have the possibility to unlocking some secrets of the deep space. together with the electronics delivered by Microgate.
Fantastic. Well, you'll have to come back and tell us what those secrets are. And Andrea, was there anything else you wanted to add?
I want to just to join Gerald in this to help humanity in general to discover the secret of the universe and let this discover to improve our life in general. And again, I want to thanks very much, Gerald, for all the support and also the collaboration.
Well, thank you both very much. I think it's clear to see that Vicor and Microgate are working extremely well together. And thank you both very much for taking the time to chat with me about the project and the collaboration.
Thank you, Paige. Thank you, Paige.
Thank you for listening to this latest episode of Electronic Specifier Insights. Don't forget to subscribe to the series to keep up to date with our newest guests, and do share with fellow colleagues, friends and family who may be interested in the latest news from the electronics industry.
Electronic Specifier.